All right, so we're talking about mass spectrometry, and the last thing we talked about was these different types of detectors. So Faraday cups were the original detectors. They just measure the flow of the current as carried by the different ions. Then the most common detector today are the electron multipliers, or also called horns. They take and through a cone shape, amplify the signal as it bounces down, much like what we see in a photomultiplier tube. And the big thing about this one, it has gain that's adjustable just like a PMT. And when I say gain, I'm talking about amplification. Adjustable. Then the high-end instruments have something that's a little different. They use a photon-based detector, and these are the most sensitive of our detectors. And basically the way they work is they have some type of a luminescent screen, something like zinc selenide. When an ion hits that, it gives off radiation, it glows. And you simply have an optical window, and you have a PMT sitting out here. The thing that is advantage to this is the PMT is at atmospheric pressure. So if there's ever any issue with the detector, you don't have to vent the instrument to work on it. Secondly, if you need to cool it with liquid nitrogen to really reduce the dark current, you can do that. So you can really get good sensitivity with these. I've seen a couple of instruments that are really going to high-end CCDs because you can take a CCD and can cool it electronically. That'll probably be the newest wave. You can also do array-based detection with those. So there's a variety of different things that are new technologies that are coming out. All right. With that, we're going to start talking about the different types of mass analyzers and hopefully get through some of that today. And this is where mass spectrometry is different than some of the other techniques, because as long as we can resolve the ions, it's a mass spectrometer. But there are a lot of different ingenious ways to accomplish this, and they are very different from one another in how they do this. We classify them, number one, based on their resolution, or their ability to resolve the different M over Z's. And we define resolution as the mass divided by the difference in mass. So if you want to think of this as a single peak, we can think of it as a single peak, and it would be that mass, or it would be the average if it's multiple peaks. And we'll look at examples of both of these. So resolution that's considered low resolution, so this is the cheaper instruments. This is what we have. All right, so resolution less than 1,000. Medium resolution is somewhere in the neighborhood of 2,500 or 2,000 to 5,000. High resolution is something greater than 5,000. And then if you really want to try to do exact mass calculations, we'll talk about that at the end of the chapter, you have to have a resolution greater than 10,000. So there's two things we're looking at. One of them is how sharp the peak is, and this is what resolution is a measure of. So resolution is a measure of, if you want to think of it as a single peak, it's how sharp a single peak is. And usually you define it something, whether it's the half height or whatever that height may be. So what is the width at a certain height? So you have M being the centroid, and this would be the delta M. All right, so that's if it's a single peak. And different companies will try different tricks. So one will say, I'm defining height, my resolution at 50% height or half height. And the other one says, I'm doing it at 10%. Just be aware, if they're doing it down here, that's a better resolution of an instrument for the same number. So you've got to make sure you're comparing apples to apples with companies. There are some companies that ethically, I think it's wrong, but they are pushing their instrument as medium resolution, and in fact, they're low resolution instruments. And that's really true because everybody wants to be in this high res market, and it's really hard to accomplish. So people play tricks with the numbers. So that is the resolution that an instrument's capable of. Something that's just as important in resolution is the term at the bottom, and that's called mass accuracy. And that is how close you are to the center to where the theoretical should be. So if I say this this peak up here is, if I say that it's 280.3837 m over z, how close is that to true? All right, so mass accuracy involves that. How close is that to the true value and the error associated with that? This is just as important to be able to come up with that number out to several significant figures or decimal places as it is to getting good resolution. So we're going to talk about all these different types of instruments. So I'm just going to sum some of them here in this table. I stole it from a different textbook. Low resolution are quadrupoles and ion traps. There are 1,000 or so. That's what we have. We have 2 of those. You can have some that have an operating mode that allows them to focus in a little bit higher resolution. This is an iffy. I don't think they're really capable of doing that. Time of flight can get you up to about 10,000. High resolution time of flight can get you to 60,000. And then the Orbitrap is a new instrument that was introduced in the last 10 years. It'll get you to 100,000. And then if you want to do the ultimate, you can do FTICR. We have the coolest acronyms: Fourier transform, ion cyclotron resonance mass spectrometry. Your resolving power there can be 1 million. You're talking about 2 things that differ in the weight of an electron. Your resolution like this would be separated a distance like that. And an electron weighs 1/1640th of the mass of a proton. Okay, so you're talking about really, really high resolution. But also you've got just an idea on price tags. So 50 to 100K. And then you go to a TOF for a good high res, low res TOF, you're looking at 150 to 200. High res TOF is going to be 250 to 300. And then you start talking about the expensive stuff. Okay. So there's a meeting that's where all the instruments are sold called PittCon, Pittsburgh Conference. And it's designed for all the instrument companies get together and they do their stuff. Some of you had the opportunity to go to the ACS meeting in New Orleans. If you ever went to the showroom floor, a lot of the instrument companies have their stuff out, and they'll have things that you can see and do. There's something called, once you become a graduate student, you start to learn to live on these things, hospitality suites. And hospitality suite is that if you know the salesman, so your boss or somebody owns that instrument and you know the salesman or the service person, they'll invite you to the hospitality suite. So free liquor, okay, or free whatever. So when these companies throw a hospitality suite, they get the floor of the hotel. They'll have we went to one in Vegas where there literally was the whole calf in there that they had pit barbecued, and they were cutting off sirloins and stuff and serving them they catered, probably spent $300 or $400 a person on what they did. But when you buy these things, you're buying the technology. These Orbitrap instruments, they cost, I'm going to safely say, less than $100,000 to manufacture. You're buying the technology. So there's a lot of markup for them and an opportunity for them to. There's not one in the state of Oklahoma. There's a couple in Dallas. My colleague that was at the Noble Foundation in Ardmore, he just purchased one at the University of Missouri in Columbia for metabolomics work.
like not even make any of these until you,
Um,
or do they have some, or like how
Yeah.
does that work?
yeah, like the FTICRs are all custom made, so made to order. So anytime you get over an instrument more than like $500,000, there's not one sitting on the shelf waiting on you. So like these low end instruments, yeah, they'll stock those up, and there's not many options you can get. So, but when you get to the high end instruments, you can order them with special types of cells to do different types of analysis, and they really custom build that instrument for exactly what you want. And a lot of times, just so you understand, the lead time would be 3 years. So it's not like I'm going to order it and it's going to be here next month.
It's not Amazon.
Yeah, it's definitely not Amazon Prime. So. All right, here's the idea of resolution. So if we look at ways that we would resolve define resolution, delta M divided into M. So here you've got a peak at 500 and 501. This person's definition of resolution is at 10% height. So they measured the width at 10% height. So you had a delta of 1, which is the same as the width down here, and divide that in 500 and you get 1. Now here's another person's definition of resolution of 500, but with their instrument, they measured the peak width at half height. So if theirs was a width of 1 at half height, all you see is you barely get those two things resolved. Now both of these instruments companies say, yeah, my resolution's 500. You have to make sure under what you're buying. Okay, so the most common way that we define resolution is at half height. So if you took this resolution, do it to the half height, and measured it at half height, you'd come up with a resolution of over 1,000, so 1,040. So just, you've got to, if you ever have an opportunity to look at these, you have to really make sure you know what you're getting. Here's another example of a couple of different instruments. And a lot of these high-end instrument companies, they're catering on answering biological questions. And this drives me crazy, but it's the way it is. A lot of the people that look at the numbers, they're still stuck with the term Dalton. So instead of an atomic mass unit, from the biology side, they use the term Dalton. So 1 Dalton is what we think of as an atomic mass unit. Here's two different instruments. This is the same peptide. So on the this particular peak has this exact mass. And one instrument that's on the left, you look at the resolution that's associated with it. You take the peak width at half height, divided into the mass, and you get 903. So that's not bad, but if you look at the instrument on the right, this is a QTOF instrument. We'll talk about that as we go on. Here is a resolution of 14,500. Now the big thing is it's comparing is the centroid of this peak versus the centroid of this peak is 1 Dalton separation. Look at the separation on that one. That's what you're buying, is the confidence to say, I know that I'm looking clearly at this and not this. Here you could set a window like that and you would have 100% confidence you're looking at the right signal. Okay, so it depends on how critical it is that you get the information correct. So I want to do an example of what resolving power do you need to resolve two closely related masses. So this is the nitrogen cation. So it has a mass of 28.0061, and the carbon monoxide cation, which is 27.9949. So those are masses that are somewhat similar. So if you were going to calculate the resolution, try that again. RS is resolution. You take the average mass divided by the change in mass. So I take the two masses to get the average of them. And divide that by the difference in the masses. What'd you ever get? Did you get 500? I didn't do it, so I'm trusting y'all here. What'd you get?
I got 25.
2,500. I thought you said 500. I was going to say that's seems low. 2,500 makes a lot more sense to me. So you need an instrument to resolve those two low molar mass compounds. You need something with a resolution of 2,500. Right. So the first instrument created was called a sector instrument. And the first one was actually used magnets. So sector instruments are instruments that use combinations of magnetic and electrical sectors to resolve the ions. So you create an ion, you start with a neutral atom or molecule, you ionize it, it creates an ion. That ion is placed in an electric field, and typically the potential you're working with is in the neighborhood of thousands of volts. So you've got this ion in a vacuum, and you put it experiences a potential, let's say 5,000 volts. It accelerates so that it has a kinetic energy, 1/2 mv squared, that is equal to its charge times the charge of the electrode times the potential. This is the electrical force equation. So the ion is accelerated, and they run into this magnetic or electrical field, and what it does is it bends the ions to make a corner, and only a certain combination of mass to charge is going to be transmitted down the flat tube. So if you'll look at the picture here on the next page, so you create the ions in the source, and then all of a sudden the ions are accelerated, so they take off running in this direction. And the different three different colors here, so you've got orange versus white circles versus black circles. Those represent three different molar masses. So what happens when it runs through the magnetic field? Right-hand rule, if you've had physics, here's your magnetic field. Ions bend with respect to the right-hand field. Right-hand rule, you put your thumb along the vector, bend your hand, wrap your hand around it, and the ions will turn in this direction. Okay, so if the ions don't have enough kinetic energy, or they have too much kinetic energy, we'll use this one to represent those, they don't make the corner. They run into the walls. So you've got this tube that they want the ions to go down, and you're trying to guide them down the center of the tube so they don't hit the edge. If they ever hit the edge, they're done. And then if you have ions that have too little kinetic energy, the magnetic field bends them too much, they hit the wall on this side. It's only the ions that have the perfect amount of kinetic energy make the corner continue down to the detector. And then finally they strike some type of a detector at the end. So it filters out or separates the different ions based on the strength of this magnetic field. You scan the field to transmit different M over Z. So transmit or scan the magnetic field to transmit different M over Z. Okay. So the most common way that we use these is with a combination of both the magnetic and the electric sectors together. This is what's called a double focusing instrument. I'll show you that in a moment. These are going to be found in high resolution analyses, and you're talking about something that at minimum is going to be costing you $200,000. The downside to them, everything, you think something that costs that much, you don't want downsides, but it's got a mass range of a few thousand up to 5,000. We had one in the graduate school. In fact, it was the instrument that I worked on so much in graduate school, and the The instrument itself was 22 foot long, 6 foot wide, and that was the combination of all the sources, the electronics with it, and then the huge electromagnet, and then the big electrical sector. So the electrical sector works on the principle it's doing the same type of thing, except now you have this curved radius, and you have a positive plate on one side, a negative plate on the other, and now it attracts electrostatically. The opposites attract, so the opposites are attracted to this negative plate, and it draws them this way. The positives are repelling, so depending on the amount of the electrostatics, it's bending the ions in a similar fashion to the magnetic field. And one idea is only one M/Z is going to be transmitted through a slit or an opening down the ion path. The combination of the instruments is what we call the double sector, and you can have them in two different combinations. You can either have the magnet first, or you can have the electric sector first, and it really doesn't matter. It works either way. But the idea is that by scanning both of these things simultaneously, that from one separating component, you've got an energy plane. From the other separating component, you have a magnetic plane, and the point where those two things hit is going to be a very fine focus. It's going to be a high resolution. So when everything's perfect on this, you can determine to a very high resolution what is the mass of your compound. And the reason you have to, instruments like this are important, like to publish in Journal of Organic Chemistry. They require an exact mass of every compound. You can't just say you make something and put an IR spectra in there in NMR. They require an exact mass spectra of that organic compound. So you have to have a mass spectra that shows this is the molecular ion, and out to 4 decimal places, it exactly matches what the isotopes say it should match. So they're trying to take the question out of it. There's got to be some pretty extenuating circumstances for them to publish without it. All right, so now we get into our world, the cheap end. And I'll tell you, this is just in terms of ranking these guys, old and dying, much like I feel some days. All right, this is a technology that's not going to be around long. And it's being replaced by new, better things. Quadra poles are the most common types of instruments we have. These are an ingenious technology. The guy that developed this type of analyzer, because of the ability to miniaturize it and put it on top of a desktop instrument, he was actually awarded the Nobel Prize for his work. I got to meet him at a conference in Nashville, Tennessee at ASMS. So what it does is it transmits ions in a very small window, and they have 4 rods that one pair of rods has a radio frequency on it, the other pair of rods has a DC frequency applied to it, and you're simultaneously scanning both the RF and the DC. And when the perfect combination of RF and DC is there, an ion starts, it's being pulled in all directions by this changing signal, but it has the perfect combination and will transmit it through. Everything else gets kicked out of an orbit and hits the walls, or hits one of those rods. But as you scan this combination of DC potential on one pair of rods and the radio frequency on the other set of rods, and you do this scan, it transmits a particular M/Z at one particular point in time. These are the lower resolution instruments, but we have a couple of them. So we have one on the GCMS and both the LCMS. So the way that it works and why it has the name, if you look at the transmission that occurs in one direction, you're basically doing a cut-off filter or cut-on filter. So this is transmitting ions in the XY plane. It's not transmitting, and then it starts transmitting. In the other plane, it's a cut-off filter. So this is the YZ plane. and you are transmitting ions, and then you quit transmitting at a certain mass range. And when you put those two things together in the XYZ, so you've got all three planes there, the combination of the cut on and the cut off transmits this window of ions. Okay? And it really is, these are radio frequency controllers that you can put on side of a board inside of a laptop computer. I mean, this is controllable technology that can be miniaturized, and they can make these things really small. So quadrupoles don't require that complicated electronics by today's standard. They can transmit up to 300 M/Z, but usually you're talking about resolutions that are less than 1500, which is okay for a lot of analyses, and their cost is pretty cheap, typically somewhere in the neighborhood of 50 to 70,000. Now there's a slight variation of a quadrupole called an ion trap, and this one uses a donut-shaped ring electrode, and it has the RF radio frequency applied to it. The DC frequency is applied to the other pair of electrode, the N pair. So one side's at ground, the other side has the voltage on it. And then in this, you scan the radio frequency to destabilize and eject ions to the detector. I'll show you a picture next page, back to the rest of it. So the ions are inside of here, and they get trapped in, if you imagine, this is a toroid shape, so it's a donut sitting in the middle of this thing. All right, so it's got this type of a shape associated with it. And your ions are inside of here, and they're trapped, spinning around. All right, so they're just going in circles. And as you scan the potentials on one's at ground, the other one has a voltage to it. As you scan the potentials on this, it causes these ions to destabilize and get ejected, and it gets ejected out a hole and then goes into the detector. So you scan this potential, and you can selectively eject out different ions. Now, the reason this is called a trap by name is that you can suspend ions in here for seconds at a time. You can actually do some unique chemistries because you can create all these ions. You can throw out all the ones in a mass below, all the ones in a mass above, right? And then you could introduce something for them to run into. So they're spinning around here at high speed. You can introduce a heavy atom, something like xenon, and you've got these guys that are spinning around in here at high velocity, so this molecular ion, and all of a sudden they run into a xenon atom. It causes fragmentation. They break into pieces. And so it's like running into, throwing a brick at the thing equivalently. It's a way of doing a technique called MSMS, or breaking things up. We'll talk about MSMS in just a minute. So these, because now this whole package, what the vacuum's going to be on, this is going to be in the order of, at the largest, something like 10 centimeters by 10 centimeters by 10 centimeters. So now you're taking and pulling the vacuum on a lever instead of a large space. It's a lot easier to maintain that vacuum. It'll pump down quicker. So you've got reduced cost with the vacuum pump system. And like big instruments, so the big sector instrument we used, the vacuum pump system was $150,000. It was over half the cost of the instrument, but it had a huge footprint to pull a vacuum on. The downside to them is that the resolutions are pretty low, typically a little less than a traditional quad. You can only go up to about 1,000 M/Z, but they can do MSMS. A downside to them is that you can only put so many ions inside that little chamber, and then it gets saturated or full. So if you have something that's very high abundant signal, right? So you have a huge signal, and then you have something that's small. This huge signal will fill the whole thing up. This one gets lost. So if you have samples that are widely differing in concentration, this is not the best technique. Now, one of the downsides to it that's most significant is that the mass spectras don't always match that of other analyzers. The way that it acquires the spectra is a little bit different, so things don't exactly match up. Now, I mentioned the term MSMS. MSMS is when you take and combine two mass spectrometry analysis techniques so that the ions are transmitted from one instrument to the next. The ion trap does it a little bit differently. It ejects all the ions below a mass and then all above, and then it leaves you the one mass that's left there. In a traditional instrument, you actually have two instruments hooked back to back. That's what we call tandem mass spec, but in either case, you're doing mass spec. Today, the most commonly done is with the quadrupole. You have three quadrupoles, one that separates the ions, a second quadrupole that's for fragmentation, a third quadrupole looks at the things that you fragmented. This is called a triple quad. Triple quads start in the 300,000 to 400,000 range, go up to well over 500,000. But now they give the ability to pick needles out of the haystack. So if you're doing trace analysis, this is about as good as it gets to see very, very low concentrations. Usually with the triple quad, we talk about a term we haven't even talked about much, PPTs, part per trillions. Okay, we've talked about part per million, part per billion. PPT is 1,000 times less than that. But if you need to know something at very low concentrations, this is the way you go after it. So typically you take what's called the precursor ion, the ion of interest, and you isolate that in Q1. So that's what's being pulled out of this guy. And then you take and look at how it breaks into pieces, and you analyze that in the separate or the third quadrupole. So you look at the products, and you'll have these different fragment ions. All of the product ions are always analyzed in the third quad. So just in terms of a picture of what this thing's going to look like now, you've got the first quadrupole that gives you your first mass separation. Quadrupole 2 is what's called the collision or focusing scale. There's typically a collision gas, something like a heavy gas that you're going to introduce in here for the things to run into. And sometimes you don't even need to introduce that gas. These ions are not stable enough, they naturally decompose or decay. But if you have something like a peptide you want to break up, and if you want to see every amino acid in it, you run it into a collision gas, something like xenon, it'll break into pieces, and then you analyze those pieces in the second mass separator, which is Q3 in this, and then you go to a detection. All this is inside of one tube that's maybe 3 foot long to 4 foot long. Powerful technique. So if you could understand everything that's in this slide, you've conquered MSMS. But I just wanted to show you some terms that you might hear people talk about in publications. So these are all different ways that you can do the analysis with mass spec. So one of them is called an ion product scan. That's the way that I described it a while ago. You select in the first, this is going to be the Q1, and this is the final Q3. You take and select your first ion, and then you look at things that decompose out of that parent ion or precursor, and you scan those. All right? So another way is to look for neutral loss. So this is the product ion scan. The precursor scan is tell it, if you want to get really selected, just look at this piece. So if I want to see something that is very high sensitivity, I tell it to look for a precursor, so I scan on this end, and then I choose this ion, and then on this one I break it up again in the Q2, and then I'm looking for just this little piece or this fragment out of there. So with that, I'm basically filtering out everything else very successfully. This is the high sensitivity. So trace analysis. Where this one tells you more structural types of information. And then another one's called a neutral loss scan. If you know that there's a fragment on the molecule that may be lost, and that fragment would correspond to some component you've got a metabolite and you don't know where it's going, if you know what a piece of that metabolite that might be incorporated into other biomolecules, you can look at what loses that piece off and figure out which components that are in the instrument. And the last one is the selected reaction monitoring. So on it, what's happening is you're taking and doing a reaction, introducing a collision gas to force these things to break up, and then you're looking at specific precursor ions combined with specific fragment pairs. So we know that this is only produced from the certain piece of this guy, and you can use it for structural elucidation to try to figure out where things connected. Okay, so you can start looking at if you have, if you want to think of it in a building block format. If you fragment it and you find that you've got this piece and you can see that piece, and then you can go through and look at a fragmentation, you can look at a different piece, you can start coming with rationales and how things are put together. Okay, so all of these are a little bit more advanced beyond what we're doing in the book, or at least what we're talking about in this course, but they're different tools that give you a lot of information. Here's an example of MSMS. These are two peaks that would be found in environmental samples. Dibutyl phthalate is a common compound that we're concerned about in plasticizers, getting in the water system. It's not good for us. This is a pesticide that's used commonly on crops. So both of them have a mass of 279. So if you had a single quad or single scan, you would look at the 279 peak and you get a peak for either of them. But if you go to the MSMS and now do a precursor scan, you could do 279 and then look at the different components that are there, and you could easily identify which one of the compounds that you had. So if I wanted to do a high sensitivity analysis, what I would probably do is Q1, select the 279, Q2, look at both 149 and 205 are in the Q3, and combine those signals into one, and I could get a really high sensitivity analysis for that. In this one, I would probably use this as Q1, and in Q1 or Q3, I'd tell it to look at a combination of these three and combine the signals together. Okay, so it doesn't have to scan just at one, doesn't have to scan from low to high. You can tell it to bounce, go from one point to the other. You can switch that very, very quickly. All right. So those are things that are using the quadrupoles or the sectors. Now you start going to the things that are different types of technologies. Time of flight. What makes time of flight different is that it doesn't use an external force to separate the ions. What it does is it accelerates the ions in a high potential, and this is done with a pulse source, and then they're accelerated to get a kinetic energy in a short range, maybe a few centimeters, and they enter a field-free region where they're no longer being accelerated, and the ions drift in this open tube that's going to be anywhere from a quarter of a meter to a couple of meters long with the traditional design. Higher resolution instruments, that tube may be 10 meters long. Right. So now what happens if two ions have the same charge? That means they have the same kinetic energy. But kinetic energy, if you remember the formula for kinetic energy, I'm sure you all do, kinetic energy is a function of mass. So if they all have the kinetic energy with them, that means the way that different ions, so mass 1 is greater than mass 2 for two different ions, that means that to offset this kinetic energy, that velocity of 1 is going to be less than velocity 2, v2. If it's heavier, it goes slower. If it's lighter, it's going to go faster. So now you're looking at literally how fast it takes them to run this distance of a couple of meters. And you're measuring with a detector that now is monitoring the signal as a function of time down to a picosecond. Now, we talked about fast detectors. This was a technology they came up with in the 50s, but they didn't have detectors and electronics that could process it. It was a really low resolution until the 80s, and then it started to accelerate as electronics had become faster and faster and more integrated. It's just now it's so simple. There's no moving parts. There's nothing hardly can go wrong with these things. Your flight times are typically a few microseconds, but you're measuring those out to 6 decimal places to determine the different ions. So it requires that you have some pulse mode of ionization or sample introduction. You can't continuously be making ions, whereas the other instruments you make ions all the time. And you selectively transmit one. This one you have to make ions now, let them run down the tube, and then you're going to analyze them. So first developed in the 50s, but because of the low resolution, it's kind of put away in the closet. Better data collection, better electronics. It reemerged in the 90s, and today the resolution is limited only by the data acquisition. So standard instruments can be, and I'll say that number's even low. Standard instruments can be 100,000 today resolution, but they can do different designs, and I'll show you this how they can take it up even much higher than that. You play tricks to effectively increase your flight path. A reflectron is an ion mirror that refocuses the ions and effectively increases the flight path and increasing the resolution. So here's the simple concept. You create ions, and they start running down this tube. And what happens is the ions that are the lightest are traveling the fastest. And at some point in time, these lighter ions are going to strike the detector first. All right, so the idea is that the longer the tube, the further I let them travel, the better my resolution. I took some samples to analyze them at Texas A&M in College Station in 1996 on an Air Force grant that I was working on, because they had at that time, a high resolution mass spec. It had a 30-meter flight tube, time of flight. So literally, they knocked a hole in the wall of the lab, like a 3-foot hole, and this tube went into the lab next door. But 30 meters long. I mean, it's almost 100 feet. So they create the ions. The longer they went, the better they separated. That was the best of the technology at the time. Then some ingenious people put their hats on, and they thought, well, let's just make it run down there and turn around and come back. So what they do is they put up an electrostatic mirror on the other end where they have a series of reading electrodes. So these are just circle plates that the ions are running into, and they've got a staggered potential difference that's increasing. And they're slowly increasing it to the amount, just like you've got a photomultiplier tube and you got a voltage divider set up with the resistors. They're dividing this voltage up in a series of steps, typically 10 steps, and it's slowing the ions down, slowing them down until finally it stops them with the opposing voltage, and then it makes them run back the opposite direction. So you put it at a slight offset angle so they come in, slow down, stop, then accelerate back out, and you can make them run down the entire length of the tube again, effectively double your path length. Okay, so increase your resolution. So now instead of having to have a 30-meter tube, I can get a 5-meter tube and I can put it in, or a 10-meter tube, I can take a 5-meter tube, put it one lap. Or more effectively, we take them, put them, and make the tube run up in a room, and you can have something that's 1 meter long on an instrument. With a reflectron, it's effectively 2 meters long. And that gets you to a resolution of 100,000. But the engineers have went crazy with this. So here's a design that Joule Instruments called a spiral TOF. Okay, so this what looks like strings and some madman with a yo-yo is how they use bending mirrors to take the ions and run them through these things. They're effectively getting 100-meter flight paths So it gives an example down at the bottom. If you take a normal separation with it, so this just do the reflection with the mirror once, you get a resolution of about 1,000. Now the good thing about this is that there's no upper limit to the mask. If you wait on a heavier iron to come out, you just wait longer. It's slow, fat butt's going to get down there sometime. You just have to wait long enough. All right? And then I say, well, if I want higher resolution, I'm going to bounce it through these mirrors some, so I can get 25,000 resolution. So this is these peaks, now separated here and here. All right? And if I don't like that resolution enough, I can make it bounce through the mirrors even more, and I can get a 50,000 resolution. Okay, so this is the same distance, but see how it got sharper needle-like on that one. $500,000 instrument, but highly capable instrument. All right, I tell you, but it's going to get weirder. So there's a lot of engineering technology and just fascinating ideas that have came through and created some cool things with this technology. But it's an expensive toy. I mean, these are some of the things that, the closest one of these, there's one of these that's a former colleague of mine that I was in graduate school with, Yakub Meshif, is the national director of the metabolomics lab, carbohydrate metabolomics lab at Texas Tech. He has one of these instruments. And he's does some amazing research with those guys. Okay. We're going to continue working through mass spec. It'll probably be Monday before we finish the chapter, but that's kind of the target. And then the next chapters will be over the chromatography. So